Okay, so welcome to the last talk of today. So what I want to talk about today is a center-focused approach to cellular dynamical mean field theory. And for a short outline, so I want to very briefly introduce or reintroduce the Hubbard model. Then I want to go through the methods I'm using here, so DMFT and this real space extension, which is called CDMFT. And then I will present results of the CDMFT method on the two-dimensional square lattice, as well as the two-dimensional triangular lattice. Okay, but as I said, let me very quickly go through the introduction of the Hubbard model. So the Hubbard model is the simplest model to study effects of electron-electron correlations and includes basically two main parts. So on the one side, this kinetic energy term Tij, which allows the electrons to move around the lattice from side to side. And if two electrons are found on the same lattice side with opposite spin, they have to pay this energy cost of U, which is the so-called Hubbard interaction. Another question one can ask is like, why is this Hubbard model of such interest, even though it's very simple to understand and to write down? So one thing we can do is we can take a look at the cuprate phase diagram, which is obtained by experiments here. And we see there's a lot of different phases going on. So it's a very rich phase diagram. Besides some pseudo-gap phase and antiferromagnetic ordering, we can also find this high TC superconducting region here, which is maybe today the most prominent and interesting case. And what we also know is that today we know that the two-dimensional Hardboard model in a theoretical approach can access all of these different phases if we choose the parameters temperature and doping that we find those phases. What I want to talk about today in my talk is the special case of the undoped Hardboard model. So this is basically the situation on the right-hand side, where we can see a phase diagram for the undoped Hardboard model, where we start at a Fermi liquid regime, so a metallic state for low interactions. And by increasing the interaction for finite temperatures, we at some point find this so-called mod transition, where we transition from a Fermi liquid to a paramagnetic insulating state. So it seems that the two-dimensional Hubbard model is of large interest. So the question arises now, how can we solve this problem? Well, let me tell you, there's no exact solution known in 2 dimensions, so we kind of have to fall back onto approximations here. What we know is that DMFT, so dynamical mean field theory, provides an exact solution in infinite dimensions. And what DMFT does, it maps a lattice problem onto an effective impurity problem. And if we think about a picture, what it means is we take out one lattice side of our lattice, define this as our impurity, and then we allow the impurity to exchange electrons with an electron reservoir, which is formed by all the surrounding lattice sites. And the dynamical part of this mean field theory comes into play since we allow this impurity in time to exchange electrons with the reservoir and vice versa. So this is always a very nice picture to keep in mind while thinking about DMFT, but in terms of mathematical equations, what we in fact do is we solve the so-called self-consistency loop or the equations, which consists that we create the Weiss field. So we create the impurity model or the impurity problem. And the next step involves, solving the impurity problem. But let me tell you that step 2 is numerical very difficult. So let's just assume we can solve this impurity problem. Then we can calculate back the impurity self-energy by inverting the Dyson equation on top. And then on the last step, there comes the self-consistency condition into play, where we demand that the impurity self-energy is the same one as the lattice self-energy. And then we repeat step 1 to 4 up until the self-energy does not change anymore. Okay, so let me tell you that DMFT, even though it's an approximation in finite dimensions, for example, a two-dimensional case, was very successful to qualitatively describe the mod transition here, which is in itself very nice. It still has some severe limitations, and the biggest limitation of DMFT is that it is a purely local theory. So what we end up getting or having is the local self-energy. But what we know, for example, from cuprates and experiments like RPS experiments, is that this self-energy is not a local quantity in these materials. And this locality of this theory becomes also very problematic if we cool down to lower temperatures, where we know that long-range fluctuations play a huge role in materials like cuprates, for example. Another thing we see on first sight is that we cannot describe D-wave superconductivity with a pure DMFT approach, since it's a non-local quantity or stems from non-local fluctuations. So a lot of people in the last years and decades basically took DMFT as a starting point and tried to extend this idea of DMFT. And today there are basically two routes known. So on the one side, we see diagrammatic approaches, which includes theories like the D gamma I method or dual fermions, dual bosons. Or we can just use cluster extensions of DMFT, which on the one hand is called DCA, which is a cluster extension in momentum space. And the other extension is called CDMFT, which is the extension in real space. And that's the theory I want to talk about. So let me briefly go through the transition between DMFT and CDMFT. Well, lucky me, it's very easy to understand. So we see on the left side the situation of DMFT, where we cut out one lattice side, define this as our impurity. And now the transition to CDMFT just is the fact that we now cut out a whole impurity cluster and define this cluster as our impurity. Another good thing is that the self-consistency conditions and equations do not change. And if we solve CDMFT, what we end up with is a self-energy which has a real space dependency inside this impurity cluster. So even though our theory is based on a real space extension and we get some real space quantities out of our calculations, sometimes it's very useful to do one more post-processing step when considering CDMFT calculation. And this is the so-called paradisation. So what a paradisation does, it basically just restores the broken translational invariance of our theory by doing a Fourier transformation on this cluster impurity we cut out of our lattice. And this is sometimes needed, for example, if we want to compare our CDMFT calculation or results with experiments like RPS, for example. So let me say that we have in this paradisation one arbitrary choice, and this is which kind of quantity we use for the paradisation. So I will not go into details, but let me tell you that if I show results now, then the paradisation is always produced using the so-called cumulant paradisation, which is shown on the bottom of the slide. Okay, so this is basically the toolbox I need. So I'm doing the real space extension of DMFT, which is called CDMFT. And sometimes on top of our calculations, we do this post-processing step of the paradisation. So let me show you some results for the two-dimensional square lattice here. And I want to mention again that I'm only consider the undoped case, as well as no T prime, so no frustration in the square lattice geometry. And on this slide, we see two different phase diagrams. So on the left-hand side, basically what we see is the near temperature for different cluster sizes, where we see while increasing the cluster, we lower the surface underneath this antiferromagnetic dome, which is kind of what we expect, since our control parameter in CDMFT is basically the cluster size, where if we let this control parameter go to infinity, then of course we get the exact result. And for the exact result, we would not find any finite phase transition temperature, since we would fulfill Mermin-Wagner. Nevertheless, we see the nice effect, what we hope to see, that by increasing the cluster size, that our antiferromagnetic dome shrinks in size. So this is the left phase diagram. Let me also talk about the right one, where we see the mod transition for DMFT and different CDMFT calculations. But let me first mention that I also plotted the near temperature of DMFT in this figure on the right, just to show that we in fact have to enforce paramagnetism in our calculations to even see this mod transition. And this holds true for all the cluster sizes, not only for DMFT. But if we enforce this paramagnetism in our calculations, then we see that the slope of this mod transition changes from DMFT compared to cluster calculations, as well as if we let the temperature be constant. By increasing the cluster size, we push our critical interaction value to lower use. And that's again what we kind of expect, since we know from thermodynamical limit calculations that this critical value of U will go to zero if we push the temperature to zero. So to summarize this slide here, we see that increasing the cluster size has, so first of all, we see difference between different cluster sizes here. And of course, that the increasing of the cluster size will follow the exact solution. Another nice way to see the effect of the cluster size in CDMFT calculations is shown here on the right figure, where we see the local spectral function on the right and the lattice spectral function on a given k path on the left. So this color plot is the lattice spectral function from gamma, x, m, and then back to gamma. And let me tell you that we set the outer parameters like temperature and interactions to be constant in those calculations. The only thing we are in fact changing is the cluster size here. And what happens can be very nicely seen from the local spectral functions. So in DMFT, we start at a solution which shows a distinct quasi-particle peak. And by increasing the cluster size in our CDMFT calculations, we see that this quasi-particle peak shrinks in size, eventually falls down, and for the largest cluster sizes we have, we already see it's nearly insulating, and the two Hubbard bands are shaping up. But what really happens can be also very nicely seen in this color plot. So this gap, because there at the antinodal point, so at the X point, there's a gap appearing at a cluster size around 6 by 6. Whereas in the nodal point, this gap is not opened yet. But let me also state that we are not expecting any pseudo gap phase or behavior in this parameter regime, since I did not include any doping or T prime. The fact that the nodal point is not yet gapped just comes from the fact that our cluster is still not large enough at a size of 9 by 9. Nevertheless, what we can again see is that it's very important to consider which kind of cluster size we are calculating in the CDMFT approach. So the results I showed one slide before were obtained using this so-called paradisation method as a post-processing step. What we can also do is we can just take a look at the results which just come out from the CDMFT calculation. So we look at the spectral function here on each impurity site for an 8 by 8 cluster. And due to symmetry reason, it's actually enough to just take the upper right part of this 8 by 8 cluster to find all the important informations. And what this figure shows is actually a visualization of the breaking of the translational invariance in our CDMFT theory. And this can be seen by comparing the center side, which is on the bottom left, with this black curve represented, if you compare it to a corner side, which is the top right one. Of course, they are not the same. So this is the breaking of the translational invariance. What we also know is that at this parameter regime from numerical exact calculations, we know that the spectral function should be already insulating. So that's why we ended up saying, okay, the center side, so this black curve, is the closest to the exact solution. So we only considering the center side, and we throw out all the other sides for discussing results or looking at results here. And this is what we call the so-called center-focused idea, that we only take the center of our CDMFT calculation into consideration. And in our recent publication, we also combined this with a so-called extrapolation in cluster size, which means that since we are able to calculate different cluster sizes up to a size of 8 by 8, we can take a 1 over n fit, where n is the total number of sites in our cluster, and take a linear fit of our cluster sizes to extrapolate a quantity for infinite cluster sizes. So this quantity can be actually any quantity you choose. So it could be a self-energy, could be a Green's function, could be even a two-particle Green's function. And combining those two methods, we formed the so-called CFE method, so the center-focused extrapolation, which extracts the most accurate lattice quantities in a CDMFT approach. And I mean, of course, I also have to prove this now, since I cannot only state some random facts. And this is shown in this figure on the right here. So let me guide you through this plot. So on the top, we see the imaginary part of the self-energy for the first Matsubara point, and on the bottom, the real part. And again, we go through a closed path in the Brillouin zone from gamma xm back to gamma. And so besides periodization methods in use, the green curve here is obtained using a diagrammatic Monte Carlo approach. So the green line so the green line is our numerical exact data. So what we want to see is that our periodization idea lies within this green arrow bars here. So let me tell you that the red curve is the normal self-energy periodization used before our idea about only using the center, and it underperforms pretty heavily compared to the numerical exact data. We get closer to the exact solutions if we only consider the center in our CDMFT calculations, which is represented by the blue dash curve. And if we focus on the center only and also do an extrapolation cluster size before this, we end up within the arrow bars, which is represented here with this black line labeled as CFE. And I think with this result that we see that our idea about this new periodization method, that we lie within the arrow bars of the numeric exact calculations, I think it's a nice way to end the discussion about the square lattice. And I want to take the last few minutes to discuss CDMFT in a triangular approach.
Perfect, Marcel. You have 5 minutes left.
Okay, that's good. Okay, so the triangular lattice in the CDMFT approach, so all the theories stay the same, the equations stay the same. The situation is seen on the left side, where we take out the cluster of, we cut out the cluster of the whole lattice, which includes 7 sides, where we have one center side labeled as this red dot, and then one surrounding shell, so 6 nearest neighbors. Let me also tell you that we again only consider the paramagnetic enforced solutions and a fully frustrated system, so T prime equals T. And a very short preview, what we see is if we solve this 7-side cluster, that compared to the DMFT solution, so concerning the mod transition, we again get to lower interaction values for the same temperature. What we also see, if we take a look at this blue square in this phase diagram on the left, bottom left, that this mod transition we are labeling here is at still large temperatures. So we do not expect that we see a finite transition. It's more a crossover regime. And in the crossover regime, we can take different quantities to kind of determine where this mod transition takes place. So here are 2 possible quantities shown. So for example, the spectral weight at the Fermi energy for the center side, where we see that for low enough temperatures, we get this really nice drop of the spectral weight at some interaction values of around U equals 9. And on the right part of the slide, we see a comparison between CDMFT and DMFT at a given temperature concerning this so-called Z factor. And this comparison is pretty interesting since our cluster has 7 sites. Let me tell you, it's pretty challenging to calculate numerical results there. But one could still think, okay, it's only 7 sites, so why not only using DMFT? Why is DMFT not enough here? And this set factor really shows that, in fact, we see a huge difference between CDMFT and DMFT, where not only the slope of this set factor changes, but we also drop down to lower values of Z faster in the CDMFT approach. So to summarize, we see a huge difference between CDMFT and DMFT. Now the question arises, how good is the CDMFT approach with the 7-site cluster here? And to answer this a bit, we can again compare to diagrammatic Monte Carlo data, which is shown here, where we show the local self-energy part and the nearest neighbor part. And in the parameter regime where both theories can be converged, we are actually within error bars of diagrammatic Monte Carlo. So I would say CDMFT performs pretty nicely here. What we also see on the bottom left of this figure is that at u equals around 9, where we expect this mod transition, the non-local parts of the self-energy arise in strength. And that's kind of another hint that the mod transition appears here. Okay, so on my last slide, I also want to mention that we are not only compared our CDMFT calculations and results with diagrammatic Monte Carlo, but we also compared it with the so-called METS method. And this METS method is basically a wave function-based theory extending the DMRG idea to finite temperatures. And very nice thing here to see is that the METS is a wave function-based idea compared to diagrammatic Monte Carlo and CDMFT being a Green's function-based theory. And for the same parameters and for the same model, we see that in both cases, so for the potential and kinetic energy, we see a very nice agreement overall. In fact, I would say in the potential energy, the agreement between CDMFT and METS is actually very, very nice. Where in the kinetic energy, we see some differences, but we also have to keep in mind that in CDMFT, we restrict ourselves to paramagnetic solutions. So that's why this difference come into play. So now let me tell you also that I talked a lot about comparison between CDMFT and other methods in this triangular case. And due to time reasons, I did actually not talk about a lot of physics happening in this geometry, which is of huge interest if we, for example, think about Morey superlattices or organic salts. So you can read more about the physics and also the methods in this triangular case in the recent publication appearing already in arXiv on the bottom here. Maybe one results which the METS method found, it was that stripy spin correlations appear for finite temperatures at some coupling between 8.5 and 10.5. But as I said, if you're interested in the physics of the triangular, two-dimensional triangular Hubbard model, then you should really read this publication here. And with this, I want to come to a conclusion and I want to summarize my talk. So what I did, I was doing CDMFT calculation of the two-dimensional Hardboard model on the square and triangular lattice. And in both cases, we use this center focused idea. So we just use the center for discussing results of our calculations. And in the square lattice, I also presented this center focused extrapolation idea to improve the known paradisation methods. And a very quick outlook. So what's next for CNMFT? So what we want to do next is we want to investigate real-space dependent superconducting properties. So basically we want to solve CNMFT in a number approach. And since I talked a lot about the undoped case and no T prime in the square lattice, we obviously can also include these parameters in CDMFT, and we are already doing this. So in the recent work of our master student, Michael Meixner, we already included some results for the doped case, and you can find the results and some more informations in tomorrow's poster session at the poster number P15. So feel free to step by here. And with this, I'm finished. I want to thank you for your attention, and I want to thank all of my collaborators.